Hello everyone, and welcome. Today, we are going to explore a major breakthrough in AI reliability, ZeroReplay debugging for multi-agent LLM traces. We'll be looking at how the BranchPoint-Latent framework represents a paradigm shift by predicting counterfactual oracles via event knowledge graphs, and incredibly, doing it at zero inference cost. Let's look at the core of the problem. Reliable operation of multi-agent LLM systems requires us to debug long, complex execution traces. We know that a single failure is usually the result of cascading actions, but the actual root cause, that causally decisive event, is completely buried inside thousands of lines of unstructured noise like messages, routes, memory writes, and tool calls. To actually fix the system, we have to find the exact node where the trajectory fatally diverged. Historically, the standard tool for this job has been the counterfactual replay oracle. This involves rewinding, editing, and rerunning the trajectory to measure an event's downstream effect. While it is highly reliable, it is computationally devastating. The cost multiplies across the number of events, the interventions, and the model calls. Because debugging budgets are finite and computation is not free, exhaustive active replay is simply impossible at production scale. If we look at the current landscape of trace debugging, existing methods fall short because of their high costs. Approaches like AgDebugger and Dover rely on GPU replay and come with a very high cost. Others, like the Who and When Judge and AgenTracer 8B, rely on heavy LLM inference or RL training, making them highly expensive as well. Enter our solution, BranchPoint-Latent. By using a learned predictor, it requires zero replay and no LLMs, completing its localization task in just CPU milliseconds. So, how do we get around this cost? We make a lateral move, predict the oracle, don't run it. We are not proposing a new replay oracle. Instead, we propose a method to predict what the existing deterministic replay oracle would conclude, but without paying the massive replay cost. Given a trace and a fixed budget, our framework estimates which events the oracle would mark as high effect before any actual replay is performed. Here is our system architecture, flowing from raw logs to a final replay agenda. We take the execution trace from the multi-agent system and feed it into an event knowledge graph using cheap CPU features. This data is then passed to a gradient-boosted predictor trained with a learning-to-rank objective. The critical takeaway here is that the expensive counterfactual replay oracle is only used offline once for ground truth labels. During deployment, the expensive oracle is permanently removed, meaning no LLM calls are made during inference. To make this work without heavy text processing, we compile an event knowledge graph containing 13 specific features divided into 4 quadrants. We extract structural features like graph centrality, observable features like memory persistence, uncertainty metrics like agent disagreement, and latent features like hidden proxy payloads. Raw text logs alone are useless for cheap algorithmic prediction, and single features actually anti-correlate with the oracle. Robust prediction requires fusing all 13 of these features together. When we map out the cost accuracy frontier, the efficiency is striking. Exhaustive active replay establishes the absolute ceiling for accuracy, achieving around 91% recall but at a prohibitive cost of 11.8 oracle calls per trace. BranchPoint-Latent recovers about 80% of that active replay oracle's recall, scoring 0.731. For exactly 0% of the active replay cost. To ensure this generalizes to unseen domains, we built a meta-predictor. While a simple linear scorer peaked at a recall of 0.730, deploying a gradient-boosted model, or GBM, with a learning-to-rank objective made performance skyrocket. Across 37 trace families and over 163,000 events, our GBM hit a branch recall at 5 of 0.926, beating the previous state-of-the-art on 28 out of 37 families, all at zero replay cost. We also evaluated our LLM-free model on the Who and When leaderboard, which is the standard benchmark for failure attribution. Fitting in just seconds on a CPU, our model matched the performance of an RL fine-tuned 8B LLM, scoring 0.365 versus 0.373, and even exceeded it on the handcrafted split, scoring 0.241 versus 0.207. We deliver comparable localization at just a fraction of the cost. To understand why this approach works, we have to look at the anatomy of a trace, which typically falls into two distinct failure regimes. Regime A is graph-dominant, seen in multi-hop reasoning tasks like hotpot QA, where cheap centrality math easily wins. Regime B is tool or latent dominant, seen in coding or summarization tasks like MBPP or XSum. In regime B, centrality fails completely because the decisive events are latent tool calls with near zero centrality, meaning a simple linear weighting is entirely blind to it. You might be wondering, why not just build a cheap automatic router to look at trace statistics and decide whether to use centrality or the learned model? We call this the routing fallacy. Simple heuristics fail here because routing accuracy peaks at only 65%. The regimes simply cannot be reliably separated by structural statistics alone, and a routed policy actually underperforms the default learned model because false positives erase all the gains. Instead of manually routing, we achieve universal robustness through nonlinearity. A single gradient-boosted model natively absorbs these regime-conditional combinations. The tree interactions automatically learn the rule: use centrality unless the trace is latent or tool-heavy. This beautifully recovers the per-regime strengths without requiring any explicit router, all for the exact same ZeroReplay cost. Finally, let's establish the clear boundaries of BranchPoint-Latent. What it is: an auditable, cost-efficient decision support system, a pre-replay pre-filter to allocate scarce debugging budgets, and a knowledge-based ranker positioned on the extreme edge of the cost-accuracy frontier. What it is not a new counterfactual oracle, it is not a universal solver. Active replay still wins if you have infinite compute, and it is not a guarantee of hidden state controllability, but rather provides observability. Ultimately, it stands as a reproducible baseline for zero-cost AI reliability. Thank you.